Welcome to Module 6 of Digital Signal Processing. This module is concerned with one of the central topics of signal processing, which is sampling and interpolation. Sampling and interpolation are at the heart of interacting between the continuous time world and the discrete time world, and we're going to review all the basic concepts and prove a central theorem, which is the sampling theorem. First, we are going to think about interpolation. Now, interpolation is about as old as computation itself. And we can see an old analog device, which is called a slide rule. And we have a picture here of a slide rule that was used to compute trigonometric functions and other functions that are not easy to calculate by hand. Now, why is interpolation important? Because if you make a table of a function, and here we see an example of a table of a function, you want to know how many values you have to actually tabulate so as to have a good approximation of a function. And that's the whole theory of interpolation that we are going to review in detail for passing from a sequence to a continuous time function. Interpolation raises two interesting questions. The first one, if you have the values of a function at a number of points, how should you interpolate between these points? Should you linearly interpolate between two values? That's probably not good enough when the function is complex. The second interesting question is there a minimum set of values you need to measure the function at so that you can perfectly reconstruct it? That result is known as a sampling theorem. It's a very simple and very powerful result. Namely, if a function has a maximum frequency f0, then it is sufficient to sample the function at twice f0, and from these samples it is possible to perfectly reconstruct the function. That's a cornerstone result of signal processing. It allows to go from the continuous time world to the discrete time world and go back perfectly. Assume you have just two samples. Then it's simple enough. There is a straight line that goes perfectly through these two samples. If you have three samples, same story, you have a parabola that goes through three samples. If you have many samples, you also can try to interpolate and go through all the samples. But you can see this is a trickier issue than what we have done with two or three samples. If we have a function, we can take any samples. Let's take equally spaced samples. This will generate the sequence xn, which in this case is equal to x of n times capital T. Capital T is the spacing between two samples. So, given a sequence, we have seen how to obtain a continuous time function through a process called interpolation. So, going from the sequence to the continuous time function with interpolation. We had also seen how to start with a continuous time function and get samples through a process called sampling. The key question is, when is there a one-to-one relationship between sequences and continuous time functions? When can we go back and forth, sampling and interpolation, and these two are exact images of each other? And that's exactly the topic of the sampling theorem. We study the question of the one-to-one relationship between a band-limited function and its samples in great detail in this module. And to arrive at these results, we're going to use all the tools in the box that we have developed so far. So Hilbert spaces, projections, filtering, sinc functions, and so on. And so everything comes together here to develop this profound and very useful result. The big message of this module on sampling and interpolation can be summarized in the following points. Continuous time is the physical world, so it is a reality. It is a bit trickier than the reality of sequences and discrete times that we have seen so far. The space of band-limited functions can be very well set in a Hilbert space framework. It is a subspace of general functions, namely the ones that have no frequencies beyond the band limit. So we can use the Hilbert space geometry to define an orthonormal basis for this subspace of band-limited functions. That orthonormal basis is going to be given by the sinc function and its shifts by integer multiples of the sampling interval. And to sample a general signal, one that is not band limited, what we do is that we first project it onto the subspace of band limited functions. We do this by low-pass filtering, and then we can represent perfectly that function on this subspace. So you see that we need all the tricks that we have seen so far, we put them together, and we are able to understand in detail sampling and interpolation. The space of band-limited function is a subspace. So in R2, it would be a line going through the origin. Let's call it BL for band-limited. If a particular signal or function is band-limited, it will belong to this subspace, so it would be a vector X that lives here on the subspace, and we are going to prove the sampling theorem, which says that such a vector X can be written as a linear combination of n belonging to Z of the weighting coefficients alpha n times phi n, where phi n are the basis functions for this band-limited subspace, and we're going to see the phi n's are the sinc functions. So that's a representation theorem for band-limited functions. Now, if we have a general vector that is not band-limited, then we cannot represent it using a linear combination of sinc functions, so we have to first project it down to band-limited function. So we use a projection theorem, we find its projections x hat, and x hat now can be represented as a linear combination of sinc function. So a general function can always be band-limited, i.e. projected to the subspace of band-limited functions, and then represented perfectly. Before moving to the heart of the topic, let us briefly review its history. The Shannon sampling theorem has a very interesting history, which goes back well before Shannon. So numerical analysis people were concerned about interpolating tables of functions, and the first one to prove a version of the sampling theorem was Whittaker in England in 1915. Harry Nyquist at Bell Labs came up with a Nyquist criterion, namely that a function that had a maximum frequency f0 could be sampled at 2 times f0. In the Soviet Union, Kotelnikov proved the sampling theorem. The son of the first Whittaker, another Whittaker, further proved results on the sampling theorem. Then Herbert Rabe in Berlin in 1938 wrote his PhD thesis about the sampling theorem, but wrong time, wrong city, he got 0 credit for it. Denis Gabor worked on a version of the sampling theorem in the mid-1940s. Then Claude Shannon, the inventor of information theory, wrote a beautiful paper that is in the further reading for this class, where the Shannon sampling theorem really appears in the form that we use today. Last but not least, in 1949, Someya in Japan also proved the sampling theorem. You can see that's a very varied history. It's a very fundamental result, so many different people independently actually came up with this result.